Hello everyone, starting today we will use several videos to introduce the major paradigms of artificial intelligence. Where there are people, there are disputes and factions, and the academic world is no exception. In the realm of artificial intelligence, there are three major paradigms that cover most categories of contemporary AI. Understanding these paradigms can provide a deeper understanding of the development and achievements of artificial intelligence. It can also give a general understanding of the structure of human intelligence, thereby providing insight into the potential impact of artificial intelligence in the future. In the introduction to the history of artificial intelligence, I have already mentioned the three major paradigms: symbolism, connectionism, and behaviorism. The entanglement of symbolism and connectionism runs through the entire birth and development of modern artificial intelligence. Behaviorism only emerged in the late 20th century with its emphasis and major contributions in robot control systems. Personally, I don't quite agree with considering behaviorism as a major paradigm. The history of modern artificial intelligence is mainly a process of competition, mutual influence, and achievements between symbolism and connectionism. In my view, behaviorism is more of an auxiliary tool, not a fundamental distinction. However, many scholars list it as a separate paradigm and considering various aspects of artificial intelligence, especially perception, feedback, and machine learning. I still present it separately. I won't individually introduce other minor paradigms, such as the Bayesian and analogical reasoning approaches. Symbolism, also known as logicism, is based on the assumptions of the physical symbol system and the principle of limited rationality. It expresses concepts using logical symbols and represents the process of reasoning with logical calculus. Symbolism emphasizes logical deduction and formal systems. It has long been dominant in artificial intelligence research. Symbolism has the following characteristics. Symbol representation. Symbolism believes that intelligence can be represented by using symbols and their relationships. These symbols can represent objects, concepts, or things in the real world, and the relationships between symbols can be used to represent knowledge, logical reasoning. Symbolism emphasizes the importance of logical reasoning and believes that formal logic can be used to simulate the human reasoning process. Logical rules are used to derive new information from given symbol representations. Formal methods. Symbolism uses formal methods to represent problems and solutions as symbols and operates on them through relationships between symbols. This formalized approach makes problems clearer and more manageable. Some representative figures who contributed to the development of symbolism include Alan Turing. Although his work spanned multiple fields, his ideas profoundly influenced the symbolic direction of artificial intelligence. The concept of the Turing machine laid the foundation for the development of computer science and artificial intelligence. John McCarthy. He introduced the Lisp programming language, which had a profound impact on the field of artificial intelligence. As one of the pioneers in AI, he played a significant role in promoting symbolism. Alan Newell and Herbert A. Simon. Together, they proposed the logic theorist and early artificial intelligence program and invented the general problem-solving program. They are foundational figures in symbolism. Marvin Minsky. A pioneer in the field of artificial intelligence, Minsky, along with Simon, created early neural networks, introduced the frame theory, and made contributions to the development of both symbolism and connectionism. Symbolism has many advantages which have contributed to its long-standing dominance. In the field of artificial intelligence, clear knowledge representation. Symbolism adopts explicit symbol representation, allowing knowledge to be stored in a structured and operable manner. This aids computers in understanding and processing vast amounts of complex knowledge. Logical reasoning. Symbolism emphasizes the importance of logical reasoning, enabling precise inference using formal logic. This allows computers to engage in complex problem-solving, simulating human thought processes. Interpretability. Symbolic approaches often possess high interpretability, since symbol representations can be interpreted as specific concepts and relationships. This enables people to understand the computer's reasoning process and decision-making rationale. Formal methods. Symbolism employs formal methods to represent problems and solutions as symbols manipulated through rules. This formalized approach enhances the clarity and manageability of problem modeling. Its disadvantages are also quite apparent. Difficulty in handling uncertainty. Symbolism is relatively weak in dealing with uncertainty. In many real-world situations where information may be incomplete or vague, symbolism, relying primarily on formal logic and precise symbol representation, struggles to effectively handle such uncertainty. Difficulty in knowledge acquisition. Symbolism requires a significant amount of manual work in constructing knowledge bases, a problem known as the knowledge engineering issue. Acquiring and formalizing the knowledge of domain experts is a complex task that demands considerable time and resources. Lack of flexibility. Symbolic systems often lack flexibility when dealing with new problems or adapting to new environments. Their knowledge representations and reasoning rules are typically fixed, making it challenging to accommodate changes and evolving contexts. Computational complexity. Some symbolic methods can become computationally complex, especially when dealing with large-scale knowledge bases. This may result in low efficiency and substantial computational resource requirements. Lack of adaptability. Symbolism often lacks adaptability, performing relatively poorly in learning new knowledge or adapting to new environments. This limitation hinders symbolism from handling changes and unknown situations effectively. Semantic gap. Symbolism faces challenges in understanding natural language and addressing semantic gaps. The complexity and ambiguity of natural language make it difficult for symbolism to accurately capture the meaning of language. The aforementioned advantages and disadvantages are widely recognized in the industry. Below are some of my personal analyses. The fundamental flaw of symbolic systems lies in its theoretical foundation. Firstly, deductive logic is only a tiny part of human intelligence, far from being comprehensive or necessary. The physical reality is open-ended, so the foundational assumptions of physical symbol systems and the principle of bounded rationality in symbolism are insufficient. This is the fundamental reason for a series of shortcomings. Additionally, formal systems lack perceptual and abstraction capabilities, relying on humans to provide abstract concepts, input concepts, and fundamental rules. This leads to the knowledge engineering problem, an area where connectionism excels. Thirdly, formal systems are incomplete, as illustrated by Gödel's incompleteness theorems. Formal systems cannot complete themselves and evidently require support from other theories. Symbolic AI is no longer the hot topic and research focus in today's artificial intelligence, but it has not completely disappeared. The achievements of symbolic AI have been integrated into the entire fields of computer science and artificial intelligence. Firstly, the Prolog programming language as a predicate logic-based programming language holds its unique place and serves specific purposes in academic and applied domains. It is widely used for knowledge representation and logical reasoning in symbolic AI. Prolog supports the definition of rules and facts, making the development of expert systems more convenient. Secondly, expert systems based on rules and knowledge representation remain a very practical tool in specific domains. Thirdly, formal reasoning. Symbolic AI has propelled research in formal logic and reasoning, including formal reasoning methods such as first-order logic and model checking. These methods play a crucial role in knowledge representation and reasoning systems. Fourthly, various research outcomes of symbolic AI have become part of today's theoretical foundations in computer science. For example, formal languages are now a crucial theoretical foundation for computer programming and also provide significant assistance in natural language processing. Its influence even extends to human linguistics. In addition to the above, symbolic AI has developed numerous algorithms that are widely applied in various computer programs to solve practical problems. Examples include semantic networks and various graph algorithms, predicate logic programming, heuristic algorithms, and more.